Good morning. Today we're going to look at symmetry and dilations. This is one other transformation, and just talk about symmetry. Symmetry in two-dimensional figures, all right. A two-dimensional figure has line symmetry if the figure can be mapped onto itself by a reflection in a line called the line of symmetry. A figure in a plane has rotational symmetry if the figure can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure, called the center of symmetry. The number of times a figure maps onto itself as it rotates from 0 to 360 degrees is called the order of symmetry. The magnitude of symmetry, or angle of rotation, is the smallest angle through which a figure can be rotated so that it maps onto itself. And the magnitude can be found by taking 360 and dividing that by the order, okay? All right, and maybe I skipped the order. Oh yeah, the order right there is the number of times that it can be mapped onto itself. All right, let's go down and look at the exercises, all right? And the first three problems say, state whether the figure appears to have line symmetry, right, yes or no. If so, draw all lines of symmetry. Well, this first one definitely has a line of symmetry, and it has several. Okay, all right. You can see that first line of symmetry would be this line right here. There's a line of symmetry, all right. If you come from this vertex through the midpoint of that opposite side down there, you'll get another line of symmetry. There's another line of symmetry. So there's line 1, line 2, another one from this vertex. All right, let me draw that one in for you. All right, okay, so line 3. All right, and then there's one from this vertex going in that direction, line 4, and of course there's one from here through there. All right, and that's line 5. There are 5 lines of symmetry in that figure. All right, so the answer there is yes. For does it have one? We drew them already, and then it says state their number. Well, there are 5. Okay, all right, that next one only has one line of symmetry, and that would be this line going right between the eyes of the smiley face. All right, number 3 has no lines of symmetry, okay? All right, let's go down to number 4, 5, and 6, and let's read the instructions. The instructions say, state whether the figure has rotational symmetry, right, yes or no. If so, locate the center of symmetry and state the order and magnitude of symmetry. Well, if you were to draw in these segments, all right, I'm just going to draw in these segments right here. I'm going to just draw 2 of them. Let's draw, they want us to draw all the lines of symmetry. Well, I believe if you just draw these lines through each of those points right there, line that point up with that one right there. All right, there's a line of symmetry, and then line this one up. Okay, all right. So if you start at this point right here, okay, and you said, okay, I'm going to rotate it once, twice, 3, 4, 5, 6, 7, 8 times, all right? So the answer here is yes, it has rotational symmetry, okay? And it wants to know the order. The order is 8. Then it wants the magnitude. Well, you find the magnitude by taking 360 degrees and dividing that by 8. And 360 degrees divided by 8 is 45 degrees. So here's all 3 answers for that question. All right, let's look at the next one. And the next one does not have any rotational symmetry. So the answer here would be none. No, none. All right. The next one does have rotational symmetry, because if you were to put this line right here in there, okay, that figure could rotate about that one time. You could take this point and rotate it all the way over there. That's 180 degrees of rotational symmetry. All right, so the answer is yes, and it does it once and then again back to get back to itself. So the order is 2, and yes, 360 divided by 2 does give you 180 degrees of rotational symmetry. Okay, let's turn the page. On the next page, we talk about symmetry and three-dimensional figures. Okay, all right. A three-dimensional figure has plane symmetry if the figure can be mapped onto itself by a reflection in a plane. A three-dimensional figure has axis symmetry if the figure can be mapped onto itself by a rotation between 0 and 360 in a line. All right. So let's go talk about, let's go look at the exercises. Number 7 down there says, well, the instructions say, state whether the figure has plane symmetry, axis symmetry, both, or neither. Okay, well, if you were to put a plane through these points right here, all of those midpoints of those lateral edges on that number 7, that figure would have plane symmetry because everything would reflect about that plane and come back onto itself, all right? If you were to put a line through those 2 points right there, in other words, let's put in that line right there, that would allow you to have axis symmetry. You could rotate that figure about that one, so that one would have both plane and axis symmetry. All right, if you were to run a plane through here, all right, and I'm talking about back through that contained these 3 points, let's put 3 points on there. That plane, or that figure, would have plane symmetry, all right? And if you were to put a point here, a diameter, a line containing a diameter, that line would allow you to have axis symmetry. So that one has both as well. Okay, all right. If we were to put a plane through this point, that plane would allow that solid to reflect onto itself, so it would have plane symmetry. Now, it would not have any type of axis symmetry, so this one would just have plane symmetry, all right? If you were to put a point here, a point right in the center right there, and right here, those 3 points, the midpoints of those vertical segments, those 3 vertical segments, that means that figure would have plane symmetry, all right? But it would not have axis symmetry, I don't believe. Okay, well, unless, well, maybe if you could get a midpoint here and a midpoint there, maybe it does have both. All right, let's say it does have both. If we were to run that line through those 2 points, it would rotate 180 degrees. Let's put both. Okay, all right. This one would also have both. You could run a plane through these 3 non-collinear points. All right, or if you put the center here, and run that line through there, it would have axis symmetry. And the same is true over here. If you run this plane, you would definitely have plane symmetry. And if you put a line through those 2 points, you would have axis symmetry. So this one definitely has both. Both of these have both. All right, turn the page. All right, next we're going to look at dilations. A dilation is a similarity transformation that enlarges or reduces a figure proportionally. Dilations are completed with respect to a center point and a scale factor. And you need to remember that if the scale factor is between 0 and 1, and I'm going to write that like this, if a scale factor, I'm going to abbreviate SF for scale factor, is between 0 and 1, you have what we call a reduction. That's going to make the figure or solid or whatever smaller. All right, if your scale factor is greater than 1, then you have what we call an enlargement. Okay. All right. Let's move on to the exercises. The exercises say use a ruler to draw the image of the figure under a dilation with center S and a scale factor of R indicated. Okay, of the scale factor of R indicated. So here we're going to scale this segment up by 2. Okay, so what I'm going to do is I'm going to draw from the center of rotation a segment through point A and also through point B. Okay. All right, and now I'm going to measure, and I'm going to do A one way and B another. I'm going to do A with centimeters. Okay, so it looks like it's 1 centimeter. So when I multiply that by the scale factor 2, all right, it would go out that same ray to that point right there, 2 centimeters out there. Because from here to here, that would be A prime. So there's A prime. Now I'm going to use my compass to do the other one instead of my ruler, because you could do either one. It really doesn't matter. All right, if I measure the distance from the center of dilation to point B, I measure that distance right there. Okay, and then I mark it off not once, but twice. And that point right there will be point B prime. All right, and then all I need to do to finish this dilation is to connect, and this is A prime, excuse me. All right, A prime to B prime. Now notice that segment A prime B prime is parallel to segment AB. Also notice that it's, if you were to measure AB, segment A prime B prime is 2 of those because of the scale factor. Watch this, I'll show you. If you measure it, there's AB, you can mark off not 1, but 2 along and see that that has indeed been scaled up by a scale factor of 2. Okay, all right, let's go to the next one. The next one we're going to do a scale factor of 1/2. So we're going to reduce triangle RCT. Well, the first thing I would do is to draw a segment from the center of dilation, all right? And if it's a reduction, you don't have to go beyond each vertex. So draw just to the vertex, okay? From the center of dilation. All right. And now I'm going to measure half of each of those segments, all right? So it looks like that's about 3.8. Half of 3.8 is 1.9, I do believe. All right, so 1.9 from either endpoint, which would put you, oh, wait a minute, that's 2.8. Excuse me, that would be 1.9. 2.8 would be 1.8, 1.4, excuse me. Okay, which would put that midpoint approximately right there. Okay, all right, so that point would be point R prime. Now, as you can see, it's harder for me to measure those numbers. I could probably do it quicker if I just did a perpendicular bisector, and that's what I'm going to do with my compass. I'm just going to open up to more than half. I'm going to make a point from, and I'm going to do this for R. I'm going to put just a full circle around point S because I need that whole circle. Then I'm going to come to C and pull just what I need. I need the perpendicular bisector, and if I were to line up those two intersections, this point and that point, I could get the perpendicular bisector of segment SC. And all I need is the midpoint, so that's all I'm going to do is locate the midpoint. That will be point C prime, all right? That's the midpoint. By the way, that segment's congruent to that one. This segment right here is congruent to that one. Point C prime is the midpoint of segment CS, okay? And now I'm going to locate the midpoint of segment ST. And I've got a circle around point S with this radius that's still in my compass, as you can see. I'm going to come over here to point T and do the same thing. So, and all I need really is those two arcs right there, okay? All right, those two arcs will allow me to draw the perpendicular bisector for, and really all I need is the midpoint. That would be the midpoint of segment ST, which would be point T prime. And now I can connect T prime to R prime, okay? Connect R prime to C prime, and T prime to C prime. And triangle R prime, C prime, T prime is 1/2 the size of triangle RCT. All right, let's move on. Oh, well, if your scale factor is 1, all right, and you were to have your center of dilation here, nothing is going to change. So in other words, W is the same thing as W prime. X is the same thing as X prime. Y is the same thing as Y prime. And Z is the same point as Z prime. All right. Now let's go to number 16. We are going to draw a ray from the center of dilation, S, center S, through T and C. All right, and then we're going to measure 3 of those out. So let me get my straight edge again. There it is, okay? So from S through T, in that direction, from S through C, okay, that direction, okay. And now we're going to measure ST first, okay, and I'm going to use my compass to measure with because me trying to get those numbers off that little protractor is hard. So we're going to go out 1, 2, 3. Oh, it looks like it's at the end of that point right there. That's point T prime. Now S is the center of dilation. It will stay where it's at and become S prime. Now I'm going to measure SC. Okay, SC looks like it's about the same distance. Okay, so 1, 2, and 3, and it looks like they've already put in one of the sides of our work for us. All right, that point right there will be point C prime, and yes, triangle S prime, T prime, C prime is already there. We don't have to draw it since they did it for us. Okay, all right, let's go to number 17, 2/3, okay? All right, so I'm going to draw from S through M, and really, since it's less than 1, I've already got a segment from S to M. So what I need to do is measure it and go 2/3 of that distance SM out there. So I'm going to do that. It looks like it's 1 centimeter, and 2/3 is 0.66, which would be approximately right there. All right, now I'm going to do the same thing for SW, by the way, because it's already there. That's about 1 as well. 2/3 of that would be about 0.6, 0.7, which would be right in there. So this point right here would be point M prime. This point would be point W prime. Now I'm going to locate point P prime. Okay. By the way, S is the same thing as S prime. All right, so we'll draw the segment from the center of dilation over to point P. We'll measure it in centimeters, okay? Looks like it's about 1.7 or 1. Let's do, so we're going to do, what are we doing, 2/3? Let's do 1.6, okay? 1.6, all right, and half of 1.6. If we took, or 2/3, excuse me. If we took 2/3 of 1.6. Now, 1.6 is the same thing as 1 6/10. So that would be 2/3 of 1 6/10, which would be 2/3 of 10, 16, 16/10. Oh, 2 goes 1 time here and 5 times here. That would be 16/15, which is 1 1/15. Okay, so 1 1/15, and I'm going to have to approximate that. It's the best I can do. 1 1/15. Let's see, that's going to be about right there. The best I can do would be point P prime right there, okay? And I believe that SV is going to be the same thing because this thing looks like it's a regular polygon, all right? And yeah, I believe I'm going to go a little more than 1, 1 1, which would put me approximately right there, would be point V prime. And then I'm going to draw a segment SR, measure it. Looks like it is about 2.8, okay? 2.8 8 or one, actually 1 point, 1 point something, 1.9. Let's go 1.9. And we're going to do 2/3 of 1.9. Well, that would be 2/3 of 1.9 is 1 9/10. And 1 9/10 is the same thing as 19/10. 2 goes 1 time here and 5 times there. That's the same thing as 19/15 or 1 4/15. Okay, that's almost 1 1/4. So we're going to go about 1 1/4 out through there. 1 1/4 would be approximately right there, and that point would be R prime. Okay. All right, now I've already got segment S prime M prime. I'm going to draw segment M prime P prime, and that segment needs to be parallel to segment MP, so that kind of helps you a little bit, helps you get it close. Okay, now I'm going to draw segment P prime R prime, and that should be parallel to segment PR. That will help a little bit as well. Okay, all right, I think that's going to work for us right about there. All right, and then we connect down to V prime, and then V prime back to W prime, and then I think we have got the other two segments already there, that one and there, and we have scaled down that polygon PRVWSM, okay? All right, now this next one is the same thing as the first one, where anytime you do a scale factor of 1, it's the same figure. So G or G prime, H or H prime, J or J prime, K or K prime, F or F prime, and they all it maps back onto itself. All right, let's turn the page. On the next side, we are talk about dilations in the coordinate plane. To find the coordinates of an image after a dilation centered at the origin, multiply the x and y coordinates of each point on the pre-image by the scale factor. All right, in other words, xy changes to rx, comma, ry, if r is the scale factor. Okay, all right. And we're going to go do these examples down here, at least 2 of them. We'll try 19 to start with. So we're going to do 1/2, all right? That's your scale factor. And that means that xy is the same thing as 1/2 of x, comma, 1/2 of y. Or you can just take x divided by 2, comma, y divided by 2. And since these are all even integers, I think it'd be easier to just divide them all by 2. All right, now it wants us to graph the image and the dilation. So I'm going to graph the image first. -2 is point E, okay? -2, 4, -2, 2, 4 is point F. 2, 4, 2, 4 is point G. And 2, -2, 2, -2 is point H. So here's that figure. And you can use your straight edge if you want. It's not necessary. By the way, that's a rectangle. You have 2 horizontal and 2 vertical line segments, okay? All right. And now what we're going to do next is we're going to get these coordinates of the transform points, okay? We'll start with E prime. So take -2 and divide it by 2. That would be -1. Take the y coordinate, which is -2, and divide it by 2, and that would also be -1. All right, let's go find the coordinates of f prime. Take the x coordinate of f, which in this case is -2, and divide it by 2, or take half of it, and that would be -1. Take the y coordinate 4 and divide it by 2. 4 divided by 2 would be 2. All right, g prime would have coordinates of 2 divided by 2 for the x coordinate, which is 1, and 4 divided by 2 for the y coordinate, which is also 2. And then the last point, h prime, will have coordinates of, take the x coordinate of h and divide it by 2. 2 divided by 2 is 1. Take the y coordinate of h, -2, and divide that by 2, and you get -1. And then you can plot each of those points, okay? -1 is here. -1, +2 is here, so this is E prime. That point is F prime. All right, G prime is 1, 2, so there's G prime. And then H prime is 1, -1, so there's H prime. And then you can just connect those points, all right? And you have a dilated quadrilateral or rectangle, EFGH, by a scale factor of 1/2. All right, I want to do at least one more. Let's go do number 22, okay? All right. Well, I'm going to plot the original figure first, okay? 2, 2 is point A, so there's point A. 3, 2, so 3, 2 is point B. All right. 3, 2, did I plot that right? 3, no, excuse me. That's not right. Something didn't look right. It was too close. Okay. All right, 2, 2 is A. All right. 3, 4. So 3 and go 2, 4. There's point B right there at 3, 4. Point C is 5, 2. There's point C. So we have this horizontal segment and those two segments right there. All right, now, the rule for this dilation is that x, y changes to 2.5x, comma, 2.5y. Now, if you don't like doing decimals, which I don't, you can remember that 2.5 is the same thing as 2 5/10 or 2 1/2. And if you make it an improper fraction by doing 2 times 2 is 4 plus 1 is 5/2, then you could write that rule as xy changes to 5x divided by 2, comma, 5y divided by 2. And that's the way I prefer to write it because I can multiply by 5 and divide by 2 pretty easily, okay? All right, so I'm going to go find the coordinates of A prime, B prime, and C prime real quick by, first of all, taking the x coordinate in this, of A. I'm going to find A prime first. Take the x coordinate of A, multiply it by 5, that's 10, and divide that by 2. 10 divided by 2 is 5. All right, now that y coordinate is the same, and if you multiply that by 2 1/2, you're still going to get 5. So that was easy enough. Now we'll take the x coordinate B, multiply it by 5. 5 times 3 is 15. 15 divided by 2 is 7 1/2. So 7 1/2, all right. And now let's go find the y coordinate of B. Multiply by 5 is 20, divided by 2. 20 divided by 2 is 10. All right, let's go to C. Multiply the x coordinate by 5. 5 times 5 is 25, divided by 2 is 12 1/2. All right. Take the y coordinate, multiply it by 5. 2 times 5 is 10, divide that by 2 is 5. Okay. All right, so there are your coordinates for the triangle A prime, B prime, C prime that has been dilated with a scale factor of 2 1/2. All right, so A is at 5, 2, 4, 5, so, or A prime, I should say. There's A prime. All right, B prime is at 7 1/2, so 7 1/2, 10. So 7 1/2, 10 would be approximately right in there. There's point B prime. Okay, all right. C prime is 12 1/2. There's 13, 12 1/2, and then 5. Okay, 12 1/2, 2, 4, 5 would put you right in there. Okay, and that's C prime, and then you can connect those, and I'm going to need a straight edge. Okay, let me get my straight edge and connect those. Okay, there is triangle A prime, B prime, C prime. That is 2 1/2 times the size of triangle ABC. All right, if you have questions, please give me a call, show up in a Google Meet, or email me, whatever you need to do. Thank you. Have a good day. Bye.